Okay, so the second speaker of this session is Taitan Bo Aha from Prowler.io, and he's going to be speaking about data efficient reinforcement learning.
Right, am I mic? All right, so thanks for coming and thank you for the invitation. So I'm leading the reinforcement learning team at Prowler.io, which is a startup that I'm going to tell you a bit about today. And what I'd like to say is our main goal, we're trying to make reinforcement learning commercial. And I'll explain what I mean by that. So before I start, who knows reinforcement learning? All right, cool. Who doesn't know reinforcement learning? All right, awesome. So let's start by a motivation. So whether we are considering self-driving car industries, finance type of industries like stock market trading, logistics types of problems, robotics, or even computer games, though these problems look different at a high level, they actually share some commonality in between. And that commonality is that there's an agent, was it a car, or a trader, or a logistics central controller, or the robot itself, or the game, that's an agent that has to perform a sequence of actions in an uncertain environment in the presence of other agents. So we have an agent, it has to make decisions in an environment which we don't know up front, so we can't hand code everything. And there are typically other agents that are interacting with our controller. So not incidentally, this is the story of Prowler itself. We have three research teams in Prowler. So we have the probabilistic modeling team, which is trying to quantify the uncertainty in the environments. We have the reinforcement learning team, which is trying to get agents to make correct sequence of decisions. And then we have a multi-agent systems team, which is trying to scale reinforcement learning to strategic interactions and high number of agents. So since you know reinforcement learning, I'm going to skip fast through this. So we have agent environment, agent takes an action, environment responds by a transition state, and the reward quantifying how good that action is. As time goes by, the agent collects like a traces, a set of data, and then its goal is to learn a policy, which runs from states to actions. As it interacts over and over again, we want the agent to learn the good behavior by reinforcing the good stuff we observe and unreinforcing the bad stuff that we have seen. So, was it that you were considering a self-driving car in the environment, or Mario playing the computer game, or a robot trying to pick for you something in the kitchen? This idea prevails, and there's always an agent interacting with the environment with the goal to maximize its total reward. So maybe the most important success recently in reinforcement learning was the deep Q networks architecture that was published by DeepMind in Nature. So this is a graph from the Nature paper. And I'm sorry, this is not legible. So what we have here is a human level performance, and everything above is higher than human level performance. So they showed that if you adopt their deep Q networks architecture, in Atari games, you can outperform humans in all of these different games. So the architecture they proposed was the first time we were able to do end-to-end training in reinforcement learning. So we had an agent given a state, which is just a snapshot of the environment that was mapped through a complex loss function, a complex neural net which has convolutional and dense layers to give you Q values quantifying how good an action was. And this has also been extended by others. I think some people at Berkeley did that first, where they were able to do end-to-end learning on robots. So the main difference was, rather than having these output units to be discrete, because we have discrete actions, now we have continuous stores, right? And they were able also to train these, at least in simulation, on the PR2 and some others to make some form of a beverage for you. So those successful, these reinforcement learning algorithms require tons of millions of interactions before learning anything useful, right? So for an RL agent to do something correctly, it has to do tons of mistakes from which it would learn and then to do something correctly. So what we are interested in, however, are markets that don't allow you to make tons of mistakes. So we want, for example, to use reinforcement learning to trade. And the market is highly stochastic, so I can't really build the simulator up front to do all of my mistakes. And I don't want to wait for my reinforcement learning agent to make 10 million mistakes before it figures out the strategy, because I'll lose all my money. And therefore, what we need is we need somehow to make these techniques from RL, which have been interesting so far, actually data efficient and scalable, where we're able to learn maybe from tens of interactions with an environment and not millions of interactions with the environment. So we have got some success so far with trying to scale RL to these types of problems. And what we are building at Prowler is a decision-making platform, which is called Fugu. I have no clue why they chose Fugu, that's not my choice, but I think it means wisdom in Fijian or something, and probably a curse in some other language. But anyway, so all the technologies I'm going to describe today are actually already embedded in our platform. To better understand what's going on, let us really dig into reinforcement learning to see what's going on. What is the current practice? Why it's not working? What should we do about it? So, imagine a very simplified example where you have a reinforcement learning agent, say this dot here, and that dot has to just navigate a maze to go from this location to the goal location. Now, anyone doing reinforcement learning understands that this is a tough problem for current reinforcement learning algorithms. And the reason is, we have tons of things we can explore before getting to the dark line here, which is kind of our correct path. So before getting there, the reinforcement learning agent has to explore tons of these other dotted trajectories for it to learn that they're not good, and to, from that, infer that the good one was this thing, the black line. That being said, it's even worse because the reinforcement learning has to encounter what's going on. So I was saying even worse than that, the reinforcement learning agent not only has to encounter this thick line, but it has to encounter it often enough for it to learn something useful. I like to call this task complexity inside the reinforcement learning agent. Now, if you guys were trying to solve this problem, you would never think like a reinforcement learning agent, right? You'd never sit down and say, okay, I'm in this position, in that state, I'm going to try this position, and I'm going to see what happens. What you do is you abstract this problem to a higher level, right? You say something, okay, you know what, I'm in room 1, the ball is in room 4, so I'm going to try to exit this room, enter this room, and so forth. So what you have created in your mind is a hierarchy of this problem, and you didn't handle the problem at this low level. So now, if you don't believe that deep RL or state-of-the-art, almost state-of-the-art RL techniques cannot solve this problem, well, we have conducted an experiment. What you see here are percentage successes, right? So this is the percentage success of PQ networks or policy search to go out of a room to enter another room. So there's a 22% success rate for DQNs for it to exit room 1 and enter room 2, and so forth. Like 43% to enter this room. Even worse, it sometimes gets stuck like 35% or 80% for whole search in an irrelevant room. So I mean by we reinforcement learning researchers, we need to stop kidding ourselves. This is something useless, yeah? This is a two-dimensional problem. There are no images in there. There's nothing. It's a 2D problem, and you see it doesn't really work. So there's something not right. Let's try to crack this. So, and please note that this problem goes way beyond what I have described into, as well, games. So this is a game called Montezuma's Revenge, which is kind of the toughest Atari game where you can get 0 performance on it. Here you have an agent that is trying to get to the key by avoiding the skull. It has to get the key, then come back and open the door, one of these top doors here. So what you see here is that the agent is doing really crazy stuff, and this is after 8 million training iterations of PQ networks. So I'm not sure this is really useful. Okay. Anyways, so this is the first level of complexity I have just described, which I like to call task level complexity. But in real-world problems, there is another level of complexity that comes into play with reinforcement learning, which is the agent level complexity. So let's assume instead of having your dot, you actually have a droid. And that droid had to solve this maze problem. So apart from it being able to figure out these low-level interactions, there's a lot of coordination that has to happen in its own body, such that even if I gave it the correct path, it still knows how to walk forward before falling down. So what people are currently doing is they're taking the task complexity, they're taking the agent complexity, so rooms in a maze, agent complexity, droid, crazy dynamics. They're trying to build a convolutional type of, well, convolutional or not depends on the problem specificities, but at the end they're trying to encode it by a very big, large, deep network, and then they're trying to get more and more data with the hope that this network, as I grow it larger and larger, it'll be able to differentiate these two levels of complexity and then solve this problem. Well, clearly this solution is inefficient, and what we end up with are larger networks with more hacks, and they don't really necessarily scale and do well in real-world applications. What we are trying to do, however, is we're trying to follow a different strategy. So we're trying to divide the problem, we're trying to divide the task and the agent level complexities. We're trying to modularize the solution of each of these, and then we're trying to collate them back together to solve the original problem. So I'm going to describe two ways we do that, and that have shown improvement so far. So the work I'm going to discuss today, so some of it has gotten accepted in the HCAR last year, and we just recently got a paper at NIPS accepted, so I'm also going to present a bit of that. And the first technique I'm going to talk about is something we call divide and conquer, that is geared to handle the task complexities. So let us go back to our maze problem, and as you agree with me, when you try to solve this problem, you don't actually consider the problem at its lowest level. What you do is you try to build abstractness, you try to build abstract subgoals in your head that you want to reach, and then you chunk this problem from a holistic one big trace into smaller chunks that you can learn fast, and then you collect them together to solve the original problem. So what we're going to try to do is we're going to try to infer what are good subgoals for the agent to reach to. Once that has been done, we're going to go to our multi-agent systems team and ask them, if I know this description of the problem, can you please formulate a two-player game where you guide the agent at the low level to where it should go next? So what we're going to end up with is a meta-agent that is going to pick the subgoal for me, and then a low-level agent that is going to learn a small chunk of the big policy. As time repeats, this agent will pick the first subgoal, and now the agent in the low level will learn how to get there. Then it will feed back to the high level agent, then the high level agent will decide to pick a new subgoal for the agent to learn, and so forth. Now, interestingly, we have formulated this as a two-player game, so we also have very nice theoretical guarantees on what the policies will converge to look like. If you're interested in that, just let me know, we can discuss it further. And now the first application of this method to our maze problem reveals that following such a strategy actually does much better than BQN or policy search. So we go with HRL, the red thing you see here, is the percentage success for us. And what you see is that we are 92% capable of exiting this room, 85% entering this room, and 88% going to the goal. And most importantly, we don't get stuck in this crazy room. And the reason is because the high-level agent is also learning. Now, there's a disclaimer I need to make that for me to discover these subgoals, I did not start from scratch. This is a downside of our algorithm, but it's analogous to the AlphaGo development, first AlphaGo story, where you have some handful forms of human trajectories. From these human trajectories, we built a probabilistic model that detects switches in dynamics. So if you look at our maze problem, right, you see that, okay, you're going to go like this, as a human, you're going to play it like this, and then your dynamics switch in order to go to the next room, right? So if I'm able to detect these switches and cluster them, then I can construct high-level subgoals for the agent. Our probabilistic model is a model which has a latent state variable which is continuous, as well as a discrete set of variables which belong to finite number of subgoals. So now you end up with an intractable problem to which we employ variational inference to be able to solve that problem. The result of this is what you see here. So this is the Montezuma's revenge game. These are traces gathered from a human. And please note the traces don't have to be optimal, they have to be good enough. Why not optimal? Because there's learning happening at the high level. So if the high level agent is exploring, it will know I shouldn't take that trace because it leads me nowhere. Now, that being said, these are the traces we got. And then you can see that these blue dots here are actually kind of useful dots if the agent can target to go to. So upon the application of this to this game, to this Montezuma's revenge, you get these results. So here's what you saw before. This is a competing approach, and that is ours. So what we know is we can get to the key. After we get to the key, we get stuck a little bit there for some reason. Then we open the door. And this result has been attained in only 900,000 interactions with the environment and not 8 million or 2.5 million. So if I continue training this for an additional 1 million, for an additional 100,000 iterations, then I would completely avoid the stop. So this shows that we are doing something better than what others have been doing. And it also applies to robots, not just to games. Like if you have an ant, that ant is trying to navigate a maze. We can apply the same tricks that we applied before in order to allow that ant to solve the maze. And this is a graph showing these techniques are ours, where we decided just to use different meta-learning strategies. And the one you see here, which is the 8, there's this line that's 0. Everybody sees that? That's PPO, which is kind of state-of-the-art in RM. And clearly, that's not working. So all is good, and we have been able to reduce from, let's say, 10 million to 900,000, but that's still not good enough, right? We don't want to go from 9 million to 900,000. We actually want to go to tens of interactions with the environment. And that's where the other level of the problem comes in, which we referred to originally as the agent level complexity. So what we're going to employ now is we're going to employ model-based reinforcement learning to allow that agent to learn about itself, hopefully reducing the complexity even further. So to do that, we talked to our probabilistic modeling team and asked them if they can help us to develop action conditioned type of policies, type of models. So to illustrate, this is a very simple example where we have a pole on a cart, and that cart can just go back and forth, and your goal is to balance the cart in the top right position, right? Now, we are using images here, so we're using images as our input, and we are trying to see if we can learn a dynamical system using only low-level features. So what I'm trying to say is, on my input y, I give images. The dimensions of my latent variable x is just 4, because we know to learn the system we only need 4 dimensions, right? So if my model is correct, it should be able to strip from these videos just a 4-dimensional input that is useful to learn a model. So this is the result. You see, hopefully it runs. Yeah. So on one side, on the top side, you see the reconstruction, and on the bottom side, you see the ground truth. And you can see that we are able to learn the dynamics of this system. And interestingly, we learned what you saw from only 160 data points. So this is the first time where you have a deconvolutional network from X to Y that you are able to train by using only 160 data points. So some might argue, oh, you overfitted. Well, I think I have a backup slide with predictions that will show that we didn't really overfit, the predictions were good. So I think what happened is that our algo regularized the deconvnet much more efficiently than other techniques used like dropout and stuff like that. In any case, given this model, let's go back to what I have. So let us create the following. So let us gather traces using some policy, say it's random policy. Let us train the model that I just showed you before using these traces. Let us update the policy based on this model by doing backprop through time. And let us repeat. And the question is, will that allow me to train such type of systems more efficiently? So here's the result of that. On the x-axis, you see episodes, right? So these are number of times kind of I interact with the environment. On the y-axis, you see rewards, so higher is better. We compare ourselves against the three techniques, so PPO, TRPO, these are opening eyes, state-of-the-art policy search techniques, as well as a recent paper, I think, either from DeepMind or Sergey Levine, I'm not sure, but that paper, it does similar to what we want to do, but instead of our model, it uses a neural network. So this kind of quantifies if our model is better at prediction than the other techniques in literature. Well, please notice the log scale here. So this number that you see here is about 2,000. While for us, this number that you see here is about 15. So we were able to go, right, from 2,000 episodes to learn this system, even not fully learn it, by the way, to just 15. And now what we're going to do is we're going to try to employ such ideas in industrial applications we are considering, which I will discuss next. Yeah. Right, so now, industrial applications we are interested in, so our customers range from two markets. The first market is finance, and we are trying to create trading strategies for, to trade in market. And the other is logistics, and we are interested in taxi allocation type of problems, as well as last mile delivery types of problems. So, starting with the strategy design, what I show here, and unfortunately I can't give tons of details on how we got these results, but what I show here are just results showing our trading strategies versus the manual trading strategy. So that's what the company uses nowadays, which is the black curve. Versus standard BQM++, and when I say BQM++, I mean it's BQM plus all the tricks that were in the rainbow paper. Only actually two tricks, which are the most important tricks, the K-down conversions as well as the prioritized implement. And then what you can see here is that not only we do better than the human trading strategy, but reinforcement learning on its own, without whatever we have done, it actually either doesn't learn or it ends up losing your money. And this is actually very important to note. When you're dealing with the stock market, the only thing you have, you might have more data, but that data is just one trace in that market from the start of the market to today. Yeah? So for you to learn something useful, that is currently unrealistic for our analyst settings to do, because they need tons of exploration before learning something useful. They need to do and see new stuff. So that's why this thing doesn't do that well, and we are able to do a little bit better, and the reason is because we use like prior-based techniques and so forth. Now that being said, the other interesting customer application we have reside within the domain of resource allocation. So who knows resource allocation? All right. Well, you're at Prowler, you should know resource allocation. Okay. So in resource allocation, it's very simple. You have a set of resources that have to meet some demand. So think about it in this way. Assume you are ordering an Uber, right? And now the Uber has to dispatch a taxi for you, right? So you have the Uber, you have these resources, the taxis, you have your demands, right? Which are you ordering a taxi, you ordering a taxi, and so forth. And now Uber has to dispatch these taxis to you in an optimal way, such that you minimize your waiting time. Otherwise, you will be an unhappy customer, right? So the way to think about this is as a perfect matching, as a microtype matching problem. So here you have a set of nodes. These nodes are like the customer nodes. You, me, everybody ordering an Uber, right? These are the set of taxis available, and like where we have taxis around Madrid in some area. And then our goal is to match these customers to these taxis, but we're looking for a perfect match. So we're looking for a match which does not allow one customer to get two taxis, and we're working with kind of Uber X, if you will, like technique, where each customer should get only one taxi. So this is a combinatorial optimization problem. Well, here's a question to you. So, okay, assume you have n customers and n taxis, right? Yeah. So for the first customer node, how many taxis it can get allocated to? N. So given that you allocated that, what about the second one? M-1, third one, M-2, and so forth, right? So So you end up with M factorial possibilities, right? And that's the combinatorial problem, which our L techniques really have a hard time solving, right? To make matters even worse, this is not a static problem. It actually varies with time. As time goes by, more resources might pop up, and more customers might pop up, so more demand might pop up. So the question is, can we figure out kind of a smart strategy that would allow me to match the demand of all the customers while reducing the waiting time for each one of them? Yeah? Now, as I just described, if you are going to consider standard reinforcement learning to solve this problem, it's not really a good idea. And the reason is, as we said, we have like a combinatorial explosion in my action space, so I might need 17 years to explore all the space to give you a correct solution. What we're going to do, rather, is we're going to build a model which we call a demand model and a drop-off model. So the demand model is going to tell me what is the distribution of demand that I might have tomorrow. And the drop-off model is going to tell me where the taxi is supposed, where the customer is supposed to be dropped off after it has been picked from a certain destination. Given these models, now I'm going to be able to do model-based line RL technique because my state space is just the graph, resources, and taxis, and that is going to change according to my probabilistic model. Given that, I'm going to try to solve the RL problem, but again, not using standard RL, rather using model-based line techniques. Having applied that to the taxi allocation problem that I just described, you end up with these results. So on the x-axis here, you see an assignment strategy. On the y-axis here, you see maximum waiting time for customers. This has been conducted when we have 100 customers distributed. I think we had the map of Porto or London, I'm not sure. Now, the strategies are first come, first served, which is surprisingly was kind of used in industry nowadays. After talking to some of our customers, that's what we realized they do. The second one is first come, first served, but using the probabilistic model I talked about. So let us predict what's going to happen in the next 10 minutes, and let's do a first come, first served based on that. The other one is using RL alone, right? And the last one is using the RL-PM approach, which is this model-based like that. So you can see that we do reduce the maximum waiting times against industry standards and against any of the fields independently. This also goes beyond to when we consider 400 customers. It's a similar story. So not only we can do better, but this also tells us that the hypothesis we had at Prowler of combining these fields of PM, RL, and multi-agents is actually not such a bad idea. Each one alone doesn't do really that well, and the combination does better. So given these results, then we went to another type of problem our customers are interested in, which are package pickup and deliveries. This is the result you see here, where on the x-axis we have the number of parcels. On the y-axis is the maximal distance traveled by the trucks. So the scenario is as follows. You have a set of packages distributed in the city, and what you want is you want to dispatch your trucks such that you get all of these packages, meet a certain set of constraints such as capacity constraints. A truck cannot have 1,000 packages, as well as time constraints because maybe a package needs to be delivered by 10 a.m. tomorrow morning. And what you want to do all of that such that you maximize the distance traveled by the trucks, which kind of translates to fuel consumption by these companies. What we did is we compared ourselves against the Google OR package, which is an open source package from Google that has all these operations research-based algorithms. And what you see, you see two different types of bars. This is the maximum distance traveled using Google OR. And this is the maximum distance traveled using our technique. As the number of parcels increases, we still get a decent reduction in the distance traveled by the trucks. So next steps for this, so of course this is just the first step, right? So the next step for this is to actually make this a bit more realistic, compare against not just the OR package, but against what people currently use in industry to do these assignments. Here's an illustration. This is actually interesting. So here's an illustration on why our method works and why kind of the Google OR method more or less fails. In our method, we have a policy, right? Because we're doing our end, so we have a policy. And that policy, it has different types of actions. So some of the actions say, go pick the next parcel. Another action would say, go back to repo. And the third action would say, wait a little bit, right? Now, these actions are also delivered to the Google OR package to have more or less different comparison. Now, what you see here is that, so what are these blue things? These are parcels popping up, and these are the real parcels. These are kind of predicted parcels from our probabilistic model. So if an algorithm has knowledge of these, then it's really dumb for it to just come back to repo, go back from repo, come back to repo, and so forth. If you have a smart algorithm, and it has this kind of knowledge of what the distribution would look like the next time step, then it will actually try to create this weighting scheme, where it waits here till these parcels pop up, and so forth. Now this reduces, at least by the distance to the depot, the amount of distance traveled by the trucks. And that's why it does better, as you see here, in terms of the maximum distance traveled. Of course, I presented a very naive scenario. This is how our real data looks like. It's kind of, I don't know if anybody can read anything from this. But this is us, this is the other one, and these results are collated from this one. And that's all I had to say. So I've been at the Lombard, and we're trying to make reinforcement learning commercial. I believe just following the standard state-of-the-art literature of just taking deep-based approaches is not going to be really useful for real-world applications. And what we're trying to do is we're trying to handle that in a slightly different form by, shall I say, maybe thinking about the problem. Thank you.
We have plenty of time for questions.
I can hear you.
For the tax allocation problem, the results, yeah. So I was wondering, I mean, this problem can be formulated as an IOP to an extent, right? Do you compare against like common techniques to solve these, like Lagrangian relaxation, things like that, and relaxation?
Yeah.
Part of the different entities?
Yeah. So for this type of problem, we do not compare against these. However, we do for this type of problem. So CSP that you see here is just constraint satisfaction problem, and that's what people use in order to allocate these types of clusters. Right? Now that being said, I think it's easy to compare these. However, I just want to note one thing. When the number of passengers grows very large, or the number of taxis grows very large, I believe that machine learning techniques can help you deal with that, as opposed to OR type of techniques. Because, again, this factorial explosion, these combinatorial type of problems. So, for example, to date, the biggest DSP problem, driver salesman problem that has been solved was just 2 million, right? And if you think about it easily, you can get much larger package numbers than this if you're dealing with any medium to big-sized company, right? So, following the combinatorial track is good, but I think it's kind of exhaustive in a sense. And that's where I hope, or at least we're hoping that machine learning is offering a different view of that can scale better.
Where do you get the transition function for this method?
We model that. So we have data. So we model these. So you need the speed, yeah?
Yeah.
So we model these. So you're given data that is like timestamp data, geographical data. So for example, if you look at the Porto data set, that's exactly a data set which we use here. And then what you end up doing is just learning a probabilistic model for that. So to learn these probabilistic models, we also have to extend the state of the art a little bit, because we cannot grid, like the standard idea is just to grid and try to measure volume per, try to measure occurrences per volume, right? But if your grid is not coarse enough, then you don't get something reasonable. So for that, James and his team developed a, what was it? So the probabilistic modeling team developed a GP-based thing with a, what do they call it? A Cox process. So it was called a Cox process, right? And the Cox process is supposed to scale that kind of gridding into a continuous spectrum. And that's what we use here.
Yeah, but the results you report, is it from the model or the real?
Yeah, so which ones are you talking about? These ones. These. Yeah.
It's on the real evaluation or on the model?
Right. So let's look at first come, first serve. So this is a combination of both. So if you look at first come, first serve, that's just the real stuff, right? So you have real things happening, and you just do first come, first serve. First come, first serve PM, that is a combination of whatever real has happened and what the prediction would look like in the next time step. This guy here is predictions and real from both the model and reality. So the way this will change the graph over here is that at snapshot 1 you know the information, but then you can roll forward in time using your process. Meta learning algorithm, yeah.
How robust is the changes in the set of demonstrations?
Yeah, that's a good point. Yeah. So, okay. There are two things here, right? So, if you, I mean, it depends how bad your demonstrations are. If your demonstrations are sincerely bad, then yeah, it's not going to work. Now, if your demonstrations are great, then you get great results. If it's in between, then you get okayish results. The reason is, this high-level gun is also learning itself, right? So let's say I am simulating a track, I go like this, and like blah, 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 and then this, right? So this guy is exploring at the meta level and learning. It will arrive to the conclusion that this chunk of blah, blah, blah is useless, right? And then it will take a bit more time than what I presented, but it should be able to cope with such types of change.
When you sample these high level, it's like option, right?
Can you, I can't hear you.
So when you sample these high level goals, do they have the ending condition, or do you sample each iterator, like each interaction step?
Oh, so okay, so they don't have an ending condition, right? Because this is an option-like learning framework, right? So it has a termination condition that is learned by the feedbacks from the low-level entity.
So, but you take the second option only when the first.
Yeah, exactly. We take, but this policy of me taking the second option is not actually me. It's actually the Q values on the high level dictate that.
Yeah.
Can you say a bit more about your finance? Because you see that here versus time?
What would you like to know? What?
Well, part of the whole belief that the market is controlling signals. So knowledge that you cannot actually.
Well, I mean, okay, interesting. So I don't believe that's actually true. So in the results we're getting from the modeling aspect of things, we can see the trend in the financial market. The trend is very complicated to learn because the trend is non-stationary and variance is also time dependent. So it's not like as simple as put an LSTM on it and hope you do well, right? That wouldn't work. I mean, in fact, we tried that. It doesn't work. But you need to go into thinking about the modeling problem from a more complex perspective. So you would really like to learn the trend, but you have to notice that that trend is changing with time. So, like for example, your variance here is like this, but then something can become like this, right? So you want to end up with some types of model that can track these. Now, given that, so assume you have an accurate model. If that is there, I think the decision-making problem is not so difficult. It's still difficult, not so difficult. If you have a good model, you can do really pretty well. But the question is that how can you learn the good model? And there's a huge chunk of work happening in specifically that. Now, if you want to say that the market doesn't have any trend, at least that's not what we're saying. Maybe it depends on the type of assets or bonds here that you're interested in, but at least in the ones we're concerned with, there is a trend that you can see, and it just can be learned. And that being said, the decision problem can be solved if a good predictor exists, right? And of course, a good predictor, I don't mean a completely accurate predictor, but some good notion of prediction.
stop based on real data? Or it's
Yeah, that's based on real data. So let me describe how this works. So,
because you can actually find that you can buy a stock and you can raise the value of the stock yourself. And how do you prevent that?
yeah, so let's be careful a little bit here on how we test this algorithm, right? Okay. So we have a back tester. Yeah? So we have a back tester that is developed by our finance team. Yeah? So that back tester, it returns for you a price of time t. Now you collect the prices X amount of times, you do your RN development. Then you predict by a walk-forward window on unobserved data. Right? So this result that you see here is actually the result of predictions on unobserved data while training is happening. Right? So we don't do any naive, weird form of forward thinking or anything like that. Yes?
Could you go over the midway example?
Which one?
The one where you have an agent and then the method learning one.
Okay.
Could you explain what is happening?
This one here.
Yeah.
Okay. Okay, so here's what's happening. So you have a high-level agent that has one view of the MVP. And that view is very small. So it just sees this sub-goal, that sub-goal, this sub-goal, that sub-goal. And then you have a low-level agent that is trying to learn what the meta-agent tells it to do. So the meta-agent starts at the beginning, tells the low-level agent, go down here, go to this sub-goal, right? Now the meta-agent learns in order to arrive to that sub-goal by learning this what I call G1.
So it's that the meta-agent is seeing that there is a goal at some point, and the lower.
Yeah, so there's a goal there that the meta-agent, so the meta-agent trained, it learned the optimal policy at this high level, right? So the meta-agent said, okay, I'm going to train on this, but please notice this is a very small MVP, it's like 5 states. So then the meta-agent learns that very, very fast. After it learns that very, very fast, now it knows if I'm in this position, I should go to the next position. If I'm in this position, I should go to that position. So then it starts here, it goes here. Then once it's here, it understands from here I should go here, and so forth. Now, given its optimal policy, this policy is conditional on that. So anytime the low-level agent decides to take an action, the meta-agent tells it, look, don't try to go to the goal, but try to go here.